This is my first splash page. I'll just go over that really quick with you. What we're trying to do is share the beautiful simplicity of electronics, and hopefully have anyone who's participating discover the enchantment of electronic experimentation. So if you imagine 100 years ago, this is not long, the telegraph and the telephone were running, and there you were out in the farm. The only way you can communicate is cranking the phone over the long wires, and but then you had an old telephone with some parts in it. You were using the earphone part with some wires, and lo and behold, a crystal of gallium. And you're poking around with this earphone and the crystal, and all of a sudden you hear voices coming out of the crystal. And that to me was like, when I first had that experience as a kid, back in the 50s, it was like totally amazing. I think my eyes almost popped out of my head. That's where it begins. And this is who I am, facilitator for computers, radio, MakeHaven. I'm a retired senior engineer for National Semiconductor. Hey, there it is, Semiconductor. I guess that gives me a little credibility about semiconductors. I have an advanced extra class FCC radio license issued in 1960 while junior in high school. I won the senior division grand prize at the New England Regional Science Fair for a semiconductor transistorized solid state digital computer. Not the kind of computers that we have today. It was very primitive. It was a model. It only could do a few functions. I am now 76 years old, and I'm an ARL instructor and examiner, and I've been in electronics, computers, hardware, and software my entire adult life. There is a beautiful simplicity to all of this, and I hope to share that with you. Now, after looking over all the material that's out there in terms of basic electronic textbooks, teaching books, and online videos, I realized that I don't want to try to redo what's already been done so well. So I had to find a different way of doing this without trying to reinvent the wheel. And the way I'm going to do it is try to present some interesting experiments, simple things, and then talk about them and use them to talk about the basic functions of electronics. Brenda and I are available in the MakeHaven facilitator room on Monday and Tuesday nights from 5 o'clock to 6 o'clock. Anyone can drop in there and ask questions if you want to talk about what's in this presentation or anything else that we might be doing. Today, we're going to talk about, let's see, I got to change screens now. Hold on a minute. We're going to talk about building a crystal radio with two parts. And one part, we'll come back to this, is a diode. Here it is. Here's a symbol of a diode. And notice it has an anode and a cathode, and it has a pointer, and the cathode is like a straight bar. And the nice thing is, you probably already know about diodes. Basic functions of a diode is it allows current flow in one direction only, which immediately brings up the subject of current flow and direction. There's two things you need to know. Right off in the beginning in electronics, it got confused, Brenda says, by Benjamin Franklin, who, when he was realizing that there was a flow of current, and he assumed wrong, and he thought everything was going positive to negative. This diode shows the conventional current flow going positive to negative, positive anode, negative cathode. But in reality, electrons do not move that way. Electrons go the other way. So when you're looking at electronic circuit, you can look at it either way. You can look at it from the flow, the point of view of electron flow, or from the point of view of conventional current flow. And today, all the semiconductors that we see today will have these arrows in them, and they're all pointing in the direction of conventional current flow. So if the electrons are moving this way from cathode to anode, what is moving the other way from the anode to the cathode? And there's an answer to that. It is holes. Holes move this way. What is a hole? A hole is a atom that needs an electron to be happy. It's not a happy atom. As you know, electrons are circling the nucleus in a shell, and the shells like to have a certain number of electrons in them. And if they don't have the number of electrons that they would like to have, you could consider them. Let's put it this way. Let me say it a different way. If an atom has normally in its outer shell 2 electrons or 4 electrons, and one of them is missing, then that is a hole that if there's a loose electron anywhere, it's going to like to go in there and fill up that hole. So let me move on here. There's a schematic diagram. This is a schematic diagram of a diode. This right here is a pictorial diagram. It's a picture of a thing. It's an illustration, actually. It's not really a photo. It's just an illustration. Notice it has a bar on it, which indicates where the cathode is. So we're going to remember that conventional current flows in the direction of the arrow, and we'll stick with that notion all the way through what we talk about in electronics. I'm just looking down the line here. Here is a diode. This is very interesting. Notice there's something coming in here to this diode. And let me move on and see if we can find one that shows the opposite. Oh, here's another one. That one's a laser diode, and something's going out here. Actually, that's photons going out. And let's move down here. Let's see if we can just see a standard LED. Here it is right here. Here's a standard LED. It's a diode, and you see these arrows going out. Those are photons going out. Electrons go this way, photons go out. Up here, this is very interesting. This is a diode where photons are coming in. That's a solar cell. So if you have photovoltaic cells on your roof, all those cells are diodes. They're basically a junction. It looks like this. There's an N type and a P type, and there's a gap. And when on the solar cell, when photons from the sun hit this gap, it causes electrons to flow or current to flow. And if you were to cover the solar cell with a piece of cardboard and you played with it on the wires from it, it will act just like a regular diode. It'll only let current flow in one direction. So let me move on. And what I want to do here is take a quick look at this. Let's see. Here we go. Okay, so these are the things that every time we're into doing any kind of experimenting, we're going to try to relate it to the basics in electronics. Like you saw what a pictorial looks like, a schematic looks like, some symbol, and you're learning some jargon. We're also going to be talking about, as time goes on, and we're not going to do all this today. We're going to always, other experiments, other Monday morning events, we'll be talking about these things. Now, look at this. Look at this. Here's where all the magic is. Batteries, what are they? Magnets, crystals, and wires. This is where it's all happening. Can you imagine that? Magnets, crystals, and wires. And we're going to be coming back to that quite a bit. And then some of the basic fundamentals are, we want to talk about electrons. What are they? How do they behave? Seconds is the standard measurement of time. So we're going to be using in the world of scientific technology, we're going to be using the SI standards where time is represented in seconds. And we're going to be talking about electronic potential as being represented by volts. And then when you talk about the number of electrons flowing through a wire, we're going to be talking about amps. And when we talk about the number of resistances, things that oppose the flow of electrons, we're going to be give that a measurement term of ohms. Then we're going to talk about circuits that are closed. In other words, you got a current flow. Circuits that are open, the switch is open, nothing happens, or currents flow that has been shorted out, where the positive side of the battery hooks up to the negative side of the battery and too much current is flowing. We're shorting out the battery. Rails is another term. We'll talk about it when we get to it. We also will eventually discuss power and energy. But one of the constants that you have to know is the speed of light. And there's ways to know it. But in the SI measurement system of science, the speed of light is 300 million meters per second. Very important number. But if you were to go into the empirical system that the British created, it's 186,000 miles per second. We don't want that. We want this one. We will be talking about the speed of light right here, 300 million meters per second. Eventually, we want to talk about DC and AC, and then moving information from one point to another, which is going to be talking about frequencies, wavelengths, and eventually right here, PN junctions and semiconductors, diodes and rectifiers, photon. We're going to be in this area. So let me move on. Let's go here to, see if I got this one right. Okay, so if you're going to be into an electronic experimenter, this is the kind of basic things that you want to have available. Probably the most important place is, and I didn't put this in here, I'm going to put it in right now, is a bench. That's the most important tool. For a lot of people, it's the dining room table or the kitchen table. But you need to have a place to work. And these are the kinds of things that's really good to have available to you. Wire strippers, diagonal cutters, screwdrivers, pliers, soldering iron, and all the things that go with soldering. Solder paste, solder sucker, solder cleaning station, a solder wick, and then finally a VOM meter, a volt ohm milliamp meter. This is the analog meter where the needle moves. These are very good. They're very inexpensive. And then you got the digital voltmeters. There's no needle on them. They just give you a number on it in the screen. Then if you're going to be experimenting, assortment of resistors, coils, inductors, etc., parts. Now, there's a couple of people that are really, I'd like to point out, your reference books, I'm going to show you that next, and Google, YouTube, using Google search. There's Google and its Google Images is a very helpful resource. In fact, some of the things I've been showing you already are right off of a Google research page. But if you go to YouTube, here are two people to pay attention to. Mr. Carlson's lab, they follow this guy. He's the best electronics instructor I've ever encountered in my lifetime. He's very cool. He's also retired, and his house is like, the whole house is a laboratory. And so he's very good to watch. So check him out. But if you really want to get into nuts and bolts, the real physics and electronics, to a great instructor, this fellow right here, Matt Anderson from UCSD. He has a whole series of YouTube videos. If you want to know how an engineer thinks, he puts it right in front of you. And JR, check him out if you can, because you see him standing there, and then all of a sudden he takes out his pen and he's like writing in thin air, and you see it all on the screen. He stands in front of a black background and he just starts writing. And then he can erase the screen, and he's just writing in thin air, and we see it perfectly. He's got a really good presentation. All right, so what I'm going to do now is take a quick look over here. Let's see. Electronic. Okay, here's a set of books. Now, these books are available. You can buy them. Look, I'm going to scroll down here. You can buy these books, or you can download them as PDF files. And at MakeHaven, they are on some of the workstations there. Right in front of the electronics bench, there's 4 workstations. 1 or 2 of them have this whole collection of books in there. I got like 9 of them here. And here's another name that's really good to know is this guy, Forrest Mims. We'll come back. We'll look at his work later. But so those are resources if you want to read and you want to get a good education in electronics. Start with any of these. Let me, don't forget, there's also YouTube videos and all that good stuff. And okay, let's see, electronic. Oh yeah. Now, if you're really serious, oh, I got that. If you're really serious, check out these kits. These kits go all the way back, 50 years, some of them. But here, all the components are there, and all you got to do is add the wires, and they come with books, and they start with basic electronic circuits, and you work your way up through more and more complex circuitry. And the books not only show you a pictorial diagram, they show you a schematic diagram, and they give you instructions. This is an experimenter, especially, you might think of this only for kids. I don't think of this way. In fact, I just ordered this one off of eBay. It's particularly cool. And I'll probably get another one because I'm thinking of a kid that I want to give it to. And it comes with a book, and you can do all your basic electronics and radios, all kinds of circuits, computer circuits, counters, everything. Digital logic, analog circuits are all available. And you can pick these things up for 30, 40 bucks. So if you want to get started, this really gives you all the components you need to start experimenting. Okay, so let me move away from this now. Okay, I'm going to talk about this real quick. Now, what I tried to do was map out mathematical hierarchy. So I started up at the top, esoteric math. This has a lot to do with weird things, the math of genomics, for instance. Then under that, quantum dynamics. This is very difficult to understand because it doesn't make any sense. And then there's the notion of calculation, computer simulation, analog digital computers, digital logic, Boolean logic, calculus, probability and statistics. And I'm going through this because I'm interested in what goes on down here. Cartesian coordinates, vectors, trigonometry, geometry, algebra, multiplication, division. Notice how we're getting more and more fundamental. Addition, subtraction, number systems, positional notation, which has a lot to do with the Arab invention of the 0. Numbers, positive and negative, number lines, all kinds of numbers. And then down to counting. Remember, you were in kindergarten, you learned to count. And then what people think that was the basic. They thought that was where it all started. It's not. You go underneath counting, you have a logical calculus, and you have the notion of conversion and diversion. Then you have the logical functions, conjunction. That's the and function. If this and this is true, then this happens. You have disjunction, which says if this or this happens, then something else happens. So this is the and function, the or function. This is the exclusive or function here. And finally, down here, negation. This is a circuit where if you put a 1 in, you get a 0 out. If you put a 0 in, you get a 1 out. And basically, that is a simple, in today's terms, a transistor. The transistor will invert. You give it a signal in and it inverts it to the output. And with the notion of negation, you can build a complete digital computer. In fact, many of the supercomputers, the Cray supercomputers, it's all built with negation, inverters. You can make an AND gate out of an inverter, an OR gate, etc. So we're going to come back to this because this relates so much to semiconductor. Let's move on. So now we're going to take a look at another crystal. Crystals are so cool. So you saw where that diode only allows current to flow in one direction. We're going to use it in the radio very soon. But you got to be able to hear the signal that's coming in from the radio station. And so this is an earpiece that goes in your ear. And what's inside that earpiece? No magnets are in there. There's no coils of wire in there. All there is a crystal. And it's a piezoelectric crystal. Piezoelectric crystals. Remember, one of the fundamentals in electronics was crystals. The piezoelectric crystal, if you put a slight voltage on it, it moves. And if you reverse the voltage, it moves the other way. And so if you put an audio signal on that crystal will start vibrating, reproducing, moving some air, and reproducing the sound of music or voice coming in from a radio station. So what we're going to do is we're going to take a crystal just like this, crystal earphone like this one, and that is a semiconductor right there, right? Goes right in your ear, no magnets, no coils, and that is going to be what's going to reproduce the audio from a radio transmission that the diode is going to detect. So let me just take a quick, notice by how we found this. Went to Google, did crystal earphone. Once we got there, we hit images. And so here, Google collected images of crystal earphones from all over the internet, and here they all are. And there's some real, here, look at this one right here. So here's the crystal right here, and here's the two wires connecting it. And as a voltage, an alternating current that represents speech or music hits this crystal, this thing vibrates, and you hear it in your ear. Okay, so let's move on from there. And okay, well, while we're here, take a look at this. I'm going to see if I can zoom in on this real quick. Here is a crystal radio. Notice it has a crystal earphone. It has a crystal diode, which is going to detect the signal. Now this, and also has an antenna. Here's another symbol. That's the antenna symbol up there. And this is the ground symbol over here. We're going to ignore this part of the circuit. We're going to ignore it for now because we're not talking about that today. And this is a cool thing to talk about, though. It's truly amazing. But nonetheless, so here's an antenna. Here's a ground. Here's the diode. We don't need this. We don't need that. All we need is this crystal earphone and a diode. So if we hook the diode right here, throw everything else away, put a diode right here, earphone right here. So you hook the earphone on both sides of the diode, and then you hook an antenna on one side of the diode and a ground on the other side of the diode. And let's see, I see some other diagrams here, but that'll suffice for now. So what will happen is the radio signal, this long wire. So we got to talk about wire. So let's go to another, wires and grounds. Let me come over here and window. Let's see, earth ground. We're looking for long wire antennas. Okay. So here is what you could do. Here's your house. I mean, you can get fancy here. You can hang up a wire and run it down into where your bench is. That's what I did when I was a kid. I had a long wire in my backyard. And I'll tell you, boy, it's amazing all the radio stations I was able to get with that thing. So you could do this long wire in a variety of ways. So you could just have a long wire and stretch it out. Let's talk about what happens here in this wire. When radio stations are sending signals from all over the world, or maybe a few blocks away from your AM radio station, they're sending out electromagnetic waves. And when those waves move across this wire, they start electrons moving in the wire. So there's a lot of ways to get electrons moving in a wire. You can do it with a magnet. Just come over here with a magnet, move the magnet around the wire, and you're going to get electrons moving. But the radio frequencies of a radio station are making the electrons move. And there's like 1,000 radio stations hitting this wire at the same time. There are 1,000 radio stations on that wire coming down here into your crystal radio. And the interesting thing is those radio stations are transmitting on a frequency. Okay, what frequency? Well, we're going to talk about a couple frequencies on a regular basis. One frequency that we're going to talk about a lot is WINS New York, WINS. Now, probably anybody in Connecticut has heard WINS coming out of New York City, especially if you hang out on the beach. Everyone's playing their AM radios, which they're probably not anymore. But in the old days, you go down on the beach, there'd be 50 people listening to the radio, and they'd all be tuned into WINS. The reason why I picked that one to talk about is because it's transmitting on a frequency of 1 million vibrations per second, very close to it. It's not exactly that. If you remember, it's 1010 WINS New York. So, well, let's just say it's 10 WINS New York. Forget about the few extra. It's a little bit higher frequency than 1 megahertz. But that means that the central carrier from WINS is oscillating at 1 million times per second. And so there's a radio wave, an electromagnetic wave that's going through the atmosphere all around WINS. And when that radio wave cuts across here, it's going to create a signal, a 1 million times a second, or 1 megahertz signal is going to be in this wire. But that's not enough. WINS has to add to it the voice of the announcer or the music that they're playing. So the 1 megahertz signal would be a carrier, and who they're going to superimpose on that carrier the information. That's what communication is. You get, there's a frequency, a carrier, and then there's the information. You're going to move from point A to point B through the atmosphere without wires. So back in our crystal radio, we would have coming in on our wire a gazillion, if I can find the crystal radio again. Let me see, this is down here. Oops, not there. We're going to get to that one next. Yeah, so we'll have lots of radio stations here coming in on this wire all at the same time. And so in your crystal radio, the one that we're going to make with a single diode in one earphone, what are you going to hear? You're going to hear 1,000 radio stations at the same time. And it's a radio, you're hearing it, but actually you won't hear 1,000 radio stations at the same time, because the strongest radio station is going to overwhelm the weaker stations. So what you're going to hear in that earphone is the strongest radio station around, and we're talking about on the AM broadcast band here. So, you know, you have AM radio and FM radio. AM radio, the middle of that band is 1 megahertz. That's right about the middle is you're going to find WINS. So I told you there was going to be part of the crystal radio circuit that we're not going to talk about now. And that was the part that actually can select the radio signals that you want to listen to. But yes, just with a diode in the earphone, hooked up to a long wire antenna and connected to a ground. Okay, look over here. Here's a radio hooked up to a long wire antenna, hooked up to a ground. There's a ground symbol right there. See that little mark right there? That's one of the ground symbols. There's others. Let's see if we can spot any more up here. Looking really quick. Yeah, here's another one right here. Here, see this? That's a symbol right there. That is another symbol that you need to know. It represents ground. And there's all kinds of grounds. But in general, this symbol represents ground. So didn't the other one. And now you know what the antenna symbol looked like. It was like an upside down V. Let's see if we can see that again. someplace up here. And now look, these are all the images of radios, antennas, wires. Yeah, right here. Here you go. Here's the symbol for an antenna. Here's a symbol for a ground. So we just leave it at that. And now let's go talk about the diode itself. What's going on in this diode? And later on, after we get through this, we'll eventually start talking about LEDs that emit photons, and then special LEDs that emit lasers. There's a difference between the two. But a laser, you can have a laser diode. You can have an LED diode. You can have a radio detector diode. And some diodes are huge. You wouldn't call them a detector diode. You would call them a rectifier. And they would be able to pass huge amounts of current compared to what the signal diode. We're messing around with signal diodes now that look like this. Let's come down here. And also, if you get a chance, go to Google and just look up basic electronic symbols and look over these charts to see the various symbols. There's all kinds of great charts that show you the symbols and explain them. Right now, we don't need to know all about those right now. So we don't need to know about this anymore right now. And now, here we're looking at a ground. There's a ground symbol right there. And then here's people's feet on the ground. And then down here is we have this right outside. Looking at my computer screen. Behind my computer screen, there's a set of windows. And down on the ground, outside in the windows, I have a 6-foot copper rod pounded down deep into the ground. And that is a good ground connection. You can also get a good ground connection if you have an older house that has copper piping. You can hook up to a copper pipe. That gives you a very good ground. So you'd have a long wire strung up someplace that's going to pick up the radio signals, and they're going to come down that wire, and they're going to look to get down to ground. So all the electrons are moving inside the wire, and it's coming down to ground, and there's going to be this diode in the way. And the diode, and we're back here for a second. Here's what it was like 100 years ago when they're making the detector, diode. They found that this crystal worked better than quartz crystal. Once they started finding out the connection between crystals and electronics, they started experimenting, and all kinds of crystals. A lot of them work, but this one worked particularly good, called gallium. And what they did was they wrapped it up in lead, and they hooked a wire up to the lead, and then they poked the crystal with a little wire, and they called it a cat whisker, and that allowed it to be turned into a detector for a radio. Let me see the time. Okay. So let me see. Okay, let me go here. Watch this now. I'm going to say, I think I already have it, but I'm going to say crystal radio. I'll make it plural. Hit enter. Okay, we get a lot of stuff here, and I'm going to say, oh, okay, we're in images. So what I'll do is I'm going to look down here. These are gazillions of crystal radios that people have made. They're way more complex than the one we're making. We're just having two parts, a 1N34 diode and a crystal earphone. But look here, this was a gallium crystal right in here, and here was a wire poking it. So between here and here was a diode, and they made radios out of this. In fact, if you go back into, let me see if I can find some of the real ancient ones. After a while, the company started making crystal radios, so you can buy them already made. And they came up with here's one. Here's another one right here. Oh yeah, this is good. All right, so this was a crystal radio here and you can tune and select a radio station here. But look at right up here. Here was the cat whisker, and there was the gallium crystal right there. They did not have diodes like the 1N34 diodes that we have today. And the 1N34 diodes that we have today are made not of gallium, they're made out of germanium. And germanium works a lot better as a crystal radio detector. So what I'm going to do now is show the animation of, you can find it really quick. So far, so good. Nothing's crashed. Okay, I'll just come up here and see my windows. I should be able to get it here. Animation. So let me bring this window up. There we go. So I'm going to play this YouTube video. You will not be able to hear the voice. I'm going to make it in the future when I should play a YouTube video that you will be able to hear the audio that goes with it. But for the time being, I'll start it off way down here, and I'm going to speed it up. Working of a diode. And there's many of these, by the way. Just look at how does a diode work on YouTube. So here is a crystal, and let's say it's germanium. And what you see is there are atoms in here, and some of them need electrons. So this side has this crystal, the P-type crystal, has a lot of holes in it. What is a hole? It's an absence of an electron. On the other side, you got N-type materials. This is the cathode side. And it has a lot of atoms, but it has a lot of extra electrons. Well, that's cool. N has some extra ones. This has some holes. And you know, this really wants to get the holes filled. Let me move forward. Notice now they got a wire on both sides. So, and then this would be the arrow. This would be the cathode, the straight line. Then what did I just see? A little flash there. Okay. So let me move it forward. And this is very interesting. There's actually a voltage gradient from here to there. And when the two crystals are put together, immediately electrons start moving toward the center and holes start moving toward the center. And this area here is referred to as the gap. And the gap is very important. It has a couple of characteristics that are important. Number one, the distance from one side of the gap to the other. So that's a very, very important number, and it would be measured in micrometers or nanometers, depending on the kind of diode that we're talking about. And so remember, this is the plus side. This is the negative cathode side. So let's move it forward a little bit. So let's go ahead and look at it here. I want to start it. Please don't fail me now. Oh, this. Sorry, coming down here. Okay, let me stop it here for a second. So here what you see is the P-type material and the N-type material. This is the cathode. This is the anode, which is the big arrow. And you can see the electrons are going to go like this. They're going to flow this way. We're not showing conventional current flow. If we were showing conventional current flow, the holes would go this way. But we're showing electron flow here. So the electrons are come out this battery, through this light, lights it up here, into here, works it over here, comes through the P-type, back. And because the circuit is closed, the switch is closed, the light's going to light up, the current's going to flow in that one direction. Let's hope I can. Here we go. So now we see what's going on in this inside the diode. And notice this junction here. There's like a big area here. So let me go to a faster animation. quick preview. Okay, that's what we want to see. Let's get this stuff moving faster. There we go. So this is what's going on in that junction. So current is flowing just like this. Notice how it like has to jump across the gap. The gap. Okay, so this only allows electricity to flow in one direction. Okay, let's move on. And so if you, I'm going to stop this. And now I'm going to go over to my camera. Let's do, where do I stop it? Right here. And we won't be coming back to this. Let's just take one quick look here. Thought I saw something interesting. Yeah, here's a real simple radio. It has an antenna, a ground, the diode. But if you can imagine just hooking this diode down here and having the earphone right across the diode and still have an antenna up here and a ground here without this capacitor, this variable capacitor, or this coil, that's going to allow you to tune. But just this, the current will flow through here, through this diode, through the earphones to ground, and you will hear audio. Okay, so let's move this out of the way. Now I got to somehow get back to my presentation and switch cameras. Too many windows. How do I get to it soon, quicker? Oh, I know what I need. All I have to do is go here. Yeah. All right. So I'm going to go here, and I'm going to stop my presenting. And if you will just look at my my video. Okay. So here is my video. And here is the crystal radio. One earphone and over this pinky wire connected right across this germanium diode. There's a germanium diode. You can solder that if you want on both ends. And I'll tell you a story about this in a second. But all you need to do is hook an antenna on one side, doesn't matter, one side or the other, and the ground on the other side. And you're going to hear signal. Now, how strong a signal are you going to hear? What are you going to hear? It depends entirely how long your wire is, how much signal is able to pick up, and how close you are to a radio station. And notice you don't have to use a cat whisker. This diode is made all together. It's already done that for you. In fact, here's a whole package of germanium 1N34 diodes. Any one of these would do the job quite nicely. They're very inexpensive. You can usually buy a pack like this for $5 or $6. The costs on these things are going up. I used to buy these for 88 cents each when I was a kid. And today they're like $4 or $5 each. And unless you buy them in quantities, then they're a lot cheaper. But if you take a look at this, imagine this. Let's say you took a ballpoint pen, you took out the clicker, you took out the pen, you unscrewed the two parts, right? You had to do that to get all that out. And then you take this and put this inside the pen, and you bend this wire here. Whoops. So you put this inside the pen. Let me get these wires out of the way. You slip the whole thing inside the pen, and you bend this wire out the top of the pen and solder it to the clip. You know, the little clip that holds in your shirt pocket? And that becomes your ground. Put your thumb on it. Then you have to lengthen this wire a bit and run it down to the tip of the pen and fold it over so you have a little pointy thing sticking out. And then the fact that it was soldered to the clip on the top of the ballpoint pen, you now have put your thumb on this and go touch a long wire, and you're going to hear radio stations. Now, where I was up in Hartford when I was a kid, this is junior high school, WDRC 1360 on the radio dial was like less than a mile away, and it used to come booming in. So I could hold my thumb on this thing and touch my bed springs. And my bed springs were strong enough to give me a radio signal, and I was able to hear WDRC. And I will point something out. Wow, the quality of the sound was so beautiful. These crystals, if you stay within their voltage range, they're beautiful. How clear they are in their sound. So there was no real area here for distortion to take place. Of course, back then my hearing was much better. I don't know, today as you get older, your hearing drops off. So, okay, so that's it for now. What I want to do is I want to get to questions. Brenda just said time for questions. So let me, how do I see the questions? They're going to be.
Do you want me to read you some? They're in the
Yeah. Read them out, Jay. I appreciate the help.
Yeah. Are the crystals natural or are they manufactured?
Well, the gallium was natural. And what happened was that the cat whisker wire that you used it was oxidized metal, and that when the cat whisker touched the natural gallium crystal, then it formed the PN junction, which gave you the diode effect. There's a lot of ways to make a PN junction, but if you were to buy a 1N34 diode today, like the one that I was showing here, those are manufactured. The P material and the M material are both germanium, but when they grow the crystals, they purposely disturb. This is an interesting point. They purposely disturb the P crystal. They're going to grow a P crystal, so they add some impurities to the crystal growing. Instead of it being an absolute perfect crystal, it's got little flaws in it because it's mixed with other atoms that need electrons. So they have holes in them. On the other side, at the cathode, the same germanium is then doped with another atom that has an extra electron or two in its outer shell. And so that becomes the cathode. Now you have two germanium crystals that are grown in a laboratory or in a manufacturing, and then they put them together, and that forms the PN junction. And so it's manufactured. So the germanium crystals, you could also get a piece of germanium crystal, and if you use a cat whisker, you can get it to work also. The germanium crystal is the best one for making these kind of radios, mostly because if you remember, the gap that forms at the junction forms a little barrier, a voltage barrier in order for it to forward conduct the forward conduction energy of the electrons. We'll talk more about energy of electrons at a later date, but the energy of the electrons has to overcome that barrier. Once it overcomes that barrier, then the whole crystal switches into forward conduction. So anyway, I hope that answers the question.
Yeah, so I do have another question here. And for adding the antenna, is anything with copper useful as an antenna, or does it need to be in the shape of a long wire?
Well, what I first described here was what I would call a random length wire. And to get it up off the ground, the higher the better, the longer the better. And make sure it's not like, for instance, you wouldn't want to try to use the top pipe in your anchor fence because that pipe is connected to a vertical post, which is then hooked up to the ground. That's not going to be a really good antenna. But yeah, just a copper wire strung out, longer the better, the higher up the better. Does that answer the question?
I'll say so.
I did have the question there. I'm sorry, I didn't mean to cut you off, JR.
No, go.
Okay. So, like, say, would the same amount of copper in like ingot form also work as an antenna, or does it need to have length to it in wire form? I guess that's what I'm curious about.
Length to it.
Okay, so the length is the difference.
Yeah, it's not the amount of copper. It is the length of exposure to all the electromagnetic signals that are coming from transmitters all around the world. I mean, there are radio signals in there from Africa, from Europe, from China. Everything is on that wire.
Is
And
that why there were coiled wires in all of those radios you just showed us?
the coiled wires, you call those inductors, and a capacitor, and they form resonant circuits. They're like tuning forks.
Oh, okay.
And they will resonate at the frequency that you want to listen to, and they're so cool. A coil and a capacitor is it's an electronic tuning fork, and when the radio signal they resonate at a frequency, and when that frequency is anywhere near them, they get extremely excited. And we were talking about these signals coming in that's wired. They're relatively weak, but if you make the right kind of resonant circuit, you can make the signal a lot stronger for your diode detector and a lot stronger in your earphone by doing some magic with the coils. We'll talk about that another time. All right.
Great. So there was a question about using bed springs as antennas.
Yeah. So let me tell you, I'm glad you brought this up. So here I was as a teenager, a mile from WDRC, and experimenting with all kinds of radios. And I finally got it down to what's the fewest number of parts I can use to get a radio, and it was one diode, one earphone. And then I hooked up a wire, and then I said, what's the shortest wire I can use? That's what experimenting is about. And so I touched it to the metal window screen, which I knew was not connected to a water pipe. And then I touched it to, you remember the dialers on your telephone? You rotate the dial and then you hit this little metal stop so you don't rotate it too far. I touched it to that, and that was a really good antenna. And so I started experimenting. I brought it to grammar school, and I was hooking it up to steel inside of the fire escape, trying to find a good signal to get WDRC. But eventually, I decided I put this thing in the pen, and down the street was a Cub Scout leader, and who found out about it and asked if I would teach his Cub Scouts how to do this. So I had in the basement of my house, all these Cub Scouts came over one day, and we all made radios in the pen. And of course they worked, and the neighborhood got so close to WDRC. So we had this radio, and the strongest signal was WDRC, and that one came through pretty loud and clear. But you weren't able to tune it. And sometimes you would hear 2 or 3 stations all at once. All right.
Hey guys, that's actually not the question. Hey, I'm Phil.
I didn't get the whole way through. Yeah.
Oh my God! So that's the when you cut off the question, you don't understand what's happening.
Yeah.
So,
no, go ahead. Go ahead. Ask your question. Yeah.
Yeah. Well, anyway, there's some. I'm Philip out of West Hartford, former U.S. Navy nuclear submarines electronic technician. And good. There's some interest as to whether or not bed springs, metal bed spring, of course, could be an antenna that would capture cell phone signals that would actually cause health effects. And there actually is some research on this.
Whoa.
The avoiding antenna that you're on top of.
Yeah. But let's talk about that. First of all, and the bed spring, in my bed, in my room, 1 mile away from WDRC, that was the strongest signal coming in, at least with AM modulation. And we're talking about microvolts. You're talking about, if you want to talk about energy or power, it's minuscule. It's the same thing. Should I worry about the radiation from my cell phone? No. Should I worry about the radiation coming from my cell phone tower? No, unless you're up on the tower standing right in front of the antenna. No, out here in your house, you're okay with all that. I don't know. So I would not be worried about sitting on a metal bed spring. Now, if you're in a nuclear submarine and you got some powerful magnetic signals going on down there, I don't know what. Maybe your electric motors are radiating real strong. You might get, who knows? I mean, if it's strong enough, you might get the bed springs to weld. I don't think so.
Do you know about the guys going up in the towers, cell phone towers?
Yeah, of course.
They wear aluminum suits.
Yeah.
Yeah, they do. It's got to be reflective. They can't have that. It's going to nuke them.
you know, during the early days of radar, the radar techs up in Alaska would go stand in front of the antenna to warm up.
And also not be able to have children. And they should track them as an interesting case study as to what they would probably develop leukemia within 7 years.
Well, I don't want to make those kind of predictions, but are you telling me you're an ET on a nuke?
That's right.
On a sub?
Correct.
Ah, so you went through training at London and all that stuff? New London?
Yes, indeed. With the, well, they don't have the tower anymore, but you know what I'm saying in terms of the escape tower. They've modified how they do that. But, you know, just to make it relevant to this interesting radio presentation, 2 components and whatnot. So may I say that that a submarine is able to both navigate and communicate with a variety of different signals, right? Sure. And so one of them is, you know, we have various shortwave signals, and we also have long range radio navigation, LORAN Charlie, they would call it.
Very low frequency. You know, you could tune into all those signals right now with your computer.
Very cool. Perhaps you've heard of the Omega system.
No, but give me a little technology advisory, and I'll see if I can understand it.
So yeah, check this out. So there are literally 8 Omega. Well, previously there have been, I think there still are 8 Omega stations around the world, and they produce a like a sine wave, a peak-to-peak signal that is a quarter mile.
Very low frequency.
That's like very VLF, correct? VLF.
Totally, make the Earth is totally transparent to it.
Right, it goes right through, and then so now, so you're talking about this wire. You know, you got your receiver, and you know you got your diode, and you're listening. And now, what kind of wire do you want? Well, the submarine would have a floating wire. It's neutrally buoyant. It actually
they would drag it out, right? They would drag it out.
There's no dragging. It's unreeled.
Oh, okay. So it's vertical.
Okay. So the submarine's going through the water.
Pulling this wire.
It's not vertical. It's neutrally buoyant. All right. So then, so the sub continues, and then it spools it out, and it goes out through the tail. And then essentially it's either on the surface or right below the surface.
Yeah.
And that's where it's picking up the signal. So now you would spool out maybe 1.5 miles, 2 miles of wire, and it's going to pick up that quarter-mile signal on it.
Yeah.
How cool is that? But of course, you have to know.
Let me tell you what's cooler.
Let me just say real quick, you got to be in line with the station. Otherwise, the signal is going to hop over your wire.
Yeah. Well, let me tell you what's cooler. How about some very low frequency transmitters? They actually did this with a nuclear power station on it, pouring mega gigawatts into these low frequency antennas that are buried in the ground, and having 2 or 3 of them around the world. And by phasing them, so they were able to shoot a beam from a nuclear power station to any city they can aim it right through the planet. So
you say a beam of energy of a certain amount of wattage.
A beam of energy. They could fry a car because they all focus their very low frequency, high wattage transmissions into a single spot.
Wow. How would I learn more about that? What did they title that?
May I pause you guys for a moment? We do have 2 other questions queued up.
Okay.
So perhaps we just jump to those and then jump back to the
all right. Okay.
More conversational. So James had asked, can this 2-component radio be modified and tuned to receive cell phone signals?
Very interesting. Well, to start off with, this radio detects amplitude modulated signals. This is why I said in your AM band. It's not going to do anything for a frequency modulated signal. You're not going to hear those. But with a couple of diodes and a little bit of circuitry, you can actually make a diode FM receiver. And you could, but not this one, that you could actually hear an FM signal. But also, those FM signals today are not pure FM like in the early days of cell phone. They're digital. So they're sending pulse-coded information and in very high frequency bands. Now, there one band, let's see, did I bring one of these? Hold on a minute, I'm looking. To get to the high frequency band, this diode that we have here won't work at that higher frequency, although I do have some. I thought I brought them out. I don't see them. But they do have diodes, that radar diodes that work in the gigahertz range. But no, you're not going to hear radio stations. You're not going to hear cell phone stuff with this.
Great. And there was a second question that was, could a sculpture such as a outdoor cast iron or bronze or aluminum be used as an antenna? So could you incorporate the sculpture and the antenna together?
How tall is the sculpture?
Julia, do you want to elaborate your
This
question?
is purely theoretical. I'm talking about something that is, a large monumental scale.
Yeah, well, Julia, Julia,
a figure. Yeah.
if you know the length of the sculpture, whether it's horizontal or vertical, you can convert that length into an ideal frequency that sculpture could transmit a signal or receive a signal.
Huh.
But you got to know the length, either horizontal or vertical. And of course, it would also require a very good earth ground. But yeah, so yeah, you can get a sculpture to radiate some signal. Some antennas only need 70 centimeters long. Or here's a good one. So let's take a quick look at a 300 megahertz signal. Now, we said the speed of light was 300 million meters per second. So if you divide the 300 megahertz by the speed of light, you come out with 1 meter. That's the length of the wave. So if you had a 1 meter antenna or a half a meter antenna or a quarter of a meter antenna, all of them would work very good at 300 megahertz.
So you could get near it and it could tell you a story.
Oh, you want to have a proximity detector, so you get near it and it triggers a response.
Maybe.
Yeah, you
It's
could
all
do that.
theoretical.
You could do that. Yeah, that's that. Yeah, you definitely can do that.
And even tombstones.
Yeah, you can have a solar powered tombstone that plays the video, your last will and testimony, or how to save the world after
or a hologram.
Challenge accepted.
Yeah, and take a look at that. I mean, the photocell is a diode. The laser can come from a diode. It can come from other things too, or photons can come out. Little lights can come on. And then there's one diode that is really cool. It's called the Peltier Junction, and this is interesting because when you pass current in one direction through this diode, it gets hot on one side and cold on the other. But you reverse the current in this diode, and it gets cold on one side and hot on the other. So like it's a heat pump, depending on which way the electric. Hey, there's one right here. I took this one from the basement. This one was in a cooler. So you see, here's this big thing. I'll rotate it over. So right in the foam, this middle of this foam, there's a Peltier junction in here, and then this is a big heat sink on one side of it, and this is another heat sink on the other. So there's two heat sinks, and here's the wires from the Peltier junction right here. So all I got to do is pass current through this wire in one direction. One side of the thing's going to get hot, and the other side is going to get cold. And if I reverse the current flow, the other side will get hot, and the other side will get cold. And you can put this in the refrigerator, and they're
not seeing what it looks like. All they're seeing is the heat, the fins and whatnot. It's literally like a little square white disc that's maybe half a centimeter thick, and maybe it's 2 inch by 2 inch square. But yeah, indeed, one side frosts up and it ices. Any humidity in the air will frost on top of it, and the other side can boil water. and that's why you got the insulation in between.
I had I tried to find my Peltier Junctions. They're around someplace. We used them in at MakeHaven for one of the high school students who built a really cool apparatus. He had his heat sinks were amazing, and he had like 4 or 5 or 6 of the Peltier Junctions on there to be exactly that. In fact, it's reversible, by the way. If you were to put one of these cooling fins in hot water and the other one's in cold water, you're going to get voltage is going to come out of these 2 wires. So you can either make it hot or cold, or you can put it in wherever there's a temperature differential and get power out of these 2 wires. That's the cool thing. That's the cool thing about electronics.
Light up a little candle on it, and you can light up a light bulb from there or whatever. Yeah.
Yeah. And, you know, I had a lot. Yeah, exactly right. So, I mean, imagine putting it on an inner tube with a big black plate floating in a river someplace, and then having a heat sink in the water. So the water's flowing by, cooling the bottom, the sun's cooking the top, and you got wires hooked up to it, and it's charging your cell phones and running your computer, sitting there on the shore. You know, yeah, there's a million. Yeah. It's
so
amazing.
Coming into summer, you know, people are going to think of ways to keep cool, and they might be thinking, shoot, can I use a Peltier Junction, you know, thermal semiconductor here for like a personal air conditioner? But I will indicate, I've looked into that, believe me, a couple years ago, and it seems to say that that in fact, you know, the regular physics cooling, you can get about expansion cycle is actually more efficient than this diode setup, unfortunately.
Oh yeah, of course it is. But you know, you can get about a 60-degree rise out of the Peltier, or a 60-degree sink out of the Peltier. About a 60-degree difference between one side and the other. Not the same as your compressor. You can get a lot more out of a gasoline-driven engine than you can out of a small battery and an electric motor. It's the same thing.
Oh my goodness. We're going to have to talk about that later. I'm into electric cars.
Hey, who are you again? Tell me who you are.
I'm Phil Herder in West Hartford. U.S. Navy electronic technician, architectural engineer, and part-time inventor. Guys, you have the... I also have a Guinness World Record for the longest range electric car of 1,000 miles per charge.
Wow, pretty cool.
And I put in the comments, I'm looking for people who want to convert buses to electric.
Wow. That'd be nice.
And dump a diesel engine. Yeah.
I think it would be cool to convert an old Volkswagen bus to electric.
Well, we got to protect the school kids.
So, yeah. Rich, I hate to interrupt, but we're past 10 minutes after, and I normally try and have sort of like a concluding remark, and then you can go to more conversational format. But do you want to say anything as we close off? It looks like Julia's dropping out. Okay. Do you want to wrap it up?
Closing remark. If you're a musician, you're only as good as a musician as the amount of time you play. You got to play with it. The more you play with it, the better you get at it. Same thing here with electronics. Just play around with it. Get those experimenter kits. They're wonderful. And you know, you'd be amazed how much you can teach yourself electronics, truly. So, and hopefully you'll enjoy the enchantment of electronic experimentation. That's it for now. I'll be back next Monday with eventually we're going to get to LEDs that heal a wounded, sick body tissue. Okay.
Thank you so much, Rich. It was wonderful. I appreciate it.
So, JR, should we shut down?
Thank you. I'll stop the recording now.
Okay.
Was that?
Okay, very good. I'll hang out here if our new